And today we're going to be shifting over to talking about the ocean and also some about the air. So let's get into that. First, the Earth is 71% covered by water. It doesn't seem like it to us because we only think about the land masses. And if you look at the globe, if you look at the side of the globe that has, this is Africa. Oh, excellent. Africa, the Middle East, Asia, Europe. It seems like it's mostly land. If you look at the other side, you have over there, there's North America. South America, of course, is obscured. Here's Australia. But it's mostly water. And so, as I said, it's 51% of the Earth, or 71% is covered with water. So water's really important to how things work on the Earth, hence we're going to study it. And one of the really important things is the specific heat capacity of water. We studied this many moons ago. Okay. And we saw that there's a relationship between heat and the specific heat. C here was the specific heat, or specific heat capacity if you want to be technical. And it relates how much heat will result in how much change in temperature. So if we look at this equation just as a general rule, if C is a really big number, then delta T is going to go down for the same amount of heat that goes in or out. Right? If you have C times delta T, if C goes up, delta T goes down for the same amount of heat, Q. And so water has a large heat capacity. That means water, you can put a lot of heat in and it doesn't change the temperature much. You can take a lot of heat out and it doesn't change the temperature much. And so that makes really significant effects on our environments. So the textbook gives us a comparison between Wichita, I think that's how you spell it, Kansas, and San Francisco, California. Funny story, when we first came to America, we were only 2 hours drive from San Francisco, but we didn't know anything. My parents decided once again to take us on a vacation to see San Francisco, and my siblings and I thought it was Fran Francisco. It just made more sense to us.
When you first came to America?
Yeah.
From where?
Until I was 5, I lived in Sierra Leone. Well, 2 years in Sierra Leone, 3 years in Liberia. My parents were missionaries. So I was actually born here. My dad was already gone, but I was born in California. My mom went out when I was 5 weeks old with me. So my brother and sister are African American. I am not. So back to this. Wichita, Kansas, San Francisco, California. They're within 1 arc minute of the same latitude. So basically, they're both the same distance from the equator north. They both get, because they're same distance from the equator north, they both get the same amount of sunlight. Everything should be the same. And if you look at the temperatures, the average temperature for Wichita is the same as the average temperature for San Francisco. What's different about Wichita and San Francisco, besides the fact that San Francisco is beautiful and, has an ocean? The weather is very different. In Wichita, in the summer, what's it like? Hot.
Humid.
Is it humid too? I don't know Wichita. I just know what it said in the graphs. What about in the winter? What's it like in Wichita? Cold. Now in San Francisco, what's it like in the summer?
Dry.
Brittany's not one of my Californians, clearly.
I don't live in California.
Yes, that's the reason. You've never been there. Oh, so sad.
I live on the East Coast. You should come over.
Yeah, you should come out.
I'll come and visit you summer break.
Okay, so in San Francisco, the highest it ever gets is like 80. And now if you go inland just a little bit, like go to Oakland, it'll get a little hotter.
It's always kind of breezy there.
The coldest it ever gets in San Francisco is, I think, somewhere around 40-ish. It doesn't snow in San Francisco. I mean, it would be so rare. And the reason is the ocean. The ocean with that big body of water with its large specific heat, and Jocelyn already explained it to us, you have a lot of cold air, let's say, that comes down from the poles. That cold air, heat flows naturally from what to what? Hot to cold. So we will have heat naturally flow from the ocean into the air, warming up the air, and the ocean temperature changes just a small amount because of the large specific heat of the water. Or in the middle of summer, you get a lot of sun shining down. Ocean absorbs a lot of heat from the sun. The temperature goes up just a small amount. So being next to a big body of water, like an ocean, helps to keep the temperatures more constant throughout the year. So San Francisco gets warmer and colder. Now, some people consider a downside the fog. You get a lot of fog in San Francisco. Of course, we have some people from the Central Valley who know terms like Thule fog and know that that is really unpleasant, right? Because, you get a lot of fog there in California. I grew up in Monterey Bay Academy. It was just the way we lived. By 10 in the morning, the fog will burn off. Come 4 or 5 in the evening, the fog will roll in. It was beautiful. But that specific heat of water, the high specific heat of water, gives us the wonderful climates on the coast of California. Now, keep in mind, does California have snow? Yes. A lot of people think California is San Diego, San Francisco. If you're on the LA, yes. If you're on the coast, you have the more moderate temperatures. If you go inland, you have more variation. LA, it gets hot down in LA. Why? Well, because you're farther south still. But not as hot as it is if you go inland to, let's say, Death Valley. It gets a lot hotter there. And actually, as a result of that, we get the Santa Ana winds, right? Santa Ana winds are crazy winds that occur because of the temperature difference, which we'll get to the winds maybe today. Now, we've already learned from the last chapter about the Earth's 3 atmospheres. The primary atmosphere, the first one, was hydrogen and helium, probably. No one was here to measure, right? But based on our understanding that the solar nebula was primarily hydrogen and helium, we believe that was the first atmosphere of the Earth. Now, the textbook says the sun blew it away. The fact is, the Earth just didn't have enough gravity to hold on to those things with any kind of temperature, right? If hydrogen and helium were pretty close to absolute zero, sure, we could hold on to it. But with any kind of temperature, they just move too fast. They're above the escape velocity. So the hydrogen and helium would have to have been lost. So this is theoretical because we couldn't measure it. No one was there. But we know there should have been those gases and the Earth couldn't hold them. Then we had the secondary atmosphere, hot gases that escape through volcanoes and fissures. And the tertiary atmosphere, you had comets and stuff bringing water to the Earth. So you have a comet crash into the Earth. We have more water now. Another comet, more water. The comets are basically snowballs that form far away from the sun where you could have these volatiles stick together. And so we believe that that's what brought the water to the Earth, but then the water would take carbon dioxide out of the Earth, out of the atmosphere, and deposit it as rock. And then you have the very important cyanobacteria that metabolize carbon dioxide and water to produce carbohydrates, their energy source. And so as a result, the textbook shows it's like 6CO2. I don't remember what it's CO2 plus H2O, and there's different numbers of those yields. And it was, it's got to be, I don't remember what the coefficients are at all. It was like C6, O something, H something. I don't remember what the other numbers are, so I can't complete it. But that process plus ZO2. I don't know how many O2s either, but that process produced free oxygen, O2 gas. And that O2 gas then makes it so we have the ability for the things that go on with our lives to happen. So having the oxygen gas was a very important thing. The cyanobacteria helped to build it up, and then once you get enough oxygen gas, you start forming ozone, which helped to protect us from the ultraviolet radiation. So we've already looked at that. Let's look at the ocean. The ocean, this picture has a lot of cool information. First, we have the continental plate, and the continental plate extends out to here. So this is the continent, and this is the ocean. Now, of course, the continent did not end when water hit the continent. So you can't go to the beach and say, now I'm in North America, now I'm in the ocean, right? It's not the way it works. You would have to go out and you have a relatively flat shelf that's going out over the continent until you get to this slope. So the slope is the beginning of the transition, and the rise is where the official transition occurs. So the slope and the rise are just, the slope is where it starts, the rise is where it ends, going down. Now what's going on here is, well, we've talked about it. What's going on in this portion of the picture right here? This actually is a continuous line. Now it has faulting that split the line. A hot spot is just a single spot without the ridge. So hot spots are volcanoes. This also has lots of volcanoes. They actually call them seamounts for these underwater volcanoes. But what's the term for this, what's going on at this mid-ocean ridge? We have hot material coming up, and then what happens? Diverging. You have a rift zone, a place where the magma is coming up and convection currents are pushing the two plates apart from each other. And so new magma comes up and forms new ocean floor. So there's new ocean floor being produced here. So that's new. As you move away, it's older. And so we have the motion. Oh, that color, perfect contrast. The motion is going like that. So they're being pushed apart. I always think of Samson when I'm talking about this. The magma is pushing them apart. Then we have the abyssal plain, just the flat region of the ocean. You have the ocean floor is covered with sediment that makes it just nice and smooth for the most part in the abyssal plains. But then you have that motion is still going like this. And when the ocean floor meets the continental mass, which one is more dense? Ocean. The seafloor. And so the seafloor slides underneath the continental one, the process we call subduction. So we have that subduction. And what are all those little things where it says, well, it says continental crust, but what are all of these things in here? It's what? The trenches actually form here, but the things I circled are not trenches. They're in the vicinity, though. That's the sediment and stuff that was sitting on the basalt ocean floor, right? Stuff that settled to the bottom of the ocean that got scraped off when you had the subduction. So this is material that was transferred from the ocean floor to the continent. And remember I talked about like the islands up there in Alaska that are kind of shaped like lines because they're just scraped off stuff that was enough that it went up above sea level. So we have, well, I just like that picture because it has a lot of information. I did not mean to do that. I've just talked about all these things. I left them in here, so if you go back and look at the slides, you can have the discussion topics as well. The seafloor is largely basalt. Basalt is the magma that was about, 50% silicate, if I remember. And it's coming up out of the ground, freezing relatively quickly. If it was super quick, it would have been obsidian for the same material. If it had been much slower, it would be large crystals and something that looks more like granite. But because it's hitting water, it freezes relatively quickly. That's why it's basalt. You do have other things. You have deep canyons, trenches, and crevasses. I like to say it that way. Other things in the ocean. The abyssal plains are the flat parts. Plains, right? I always want to put an M there and think they're abysmal plains, but they're not. Abyss is in the abyss, which you probably haven't seen. The trenches are where you have the subduction zones. That's what Brittany was talking about looking at this picture. She said trenches. The trenches tend to occur in the, okay, I'm going to change the color again. So the trenches tend to occur in that location where you have the subduction. And we will look at a picture, a cross section in just a second to see those. And like I said, the seamounts are the volcanoes that are occurring there in those trenches. And I've already mentioned that. So here we have cross sections of the ocean. Notice the average depth of the ocean is 30. Okay, that was supposed to be a straight line. Is 3,800 meters. That's the average depth. Obviously, it goes deeper and shallower, but the average compared to the deepest, this Tonga Trench you can see goes way down here. The deepest point in the ocean is the Marianas Trench, which I think is 11,800 meters deep. How much is 11,800 meters? What's the highest elevation on Earth? Mount Everest, which is around 8,880 some. Let's say for friends, 9,000 meters. So that Marianas Trench goes down below sea level more than Mount Everest goes up above sea level. Now, a question that you probably don't know the answer to, what's the tallest mountain on Earth? No.
Isn't it like one underground one?
It's mostly underwater. So Mauna Kea in Hawaii, it's mostly underwater. And so it's not the highest elevation. But from the base of the mountain to the peak is the highest mountain. What would have made Mauna Kea a Hawaiian island? A volcano. It's a hot spot. That's right. That hot spot is responsible, they believe, the same hot spot for all the islands going from the Aleutian Island and the end of the Aleutian Island chain down through Hawaii. And it's still making new islands in Hawaii. Okay, so here's what we have for the seafloor. You can see the rift valleys are a little bit higher. You got some seamounts that go up pretty high. First of our clicker questions. Ocean trenches are the deepest parts of the ocean floor because, why are they the deepest parts? The picture's just the same so you can see it. Do not. Okay. Waiting on one more. There we go. Okay, so we had 5 who said that's where the oceanic crust meets the continental crust. 11 said that's where subduction occurs. 2 said no sediment accumulates in trenches. And none said all accumulated sediment settles in the abyssal plain. So we had 2 answers with a reasonable, but we had a clear, that is where subduction occurs. So let's Brittany, that was your card.
I said B.
You said B?
Yes.
And what was your reasoning?
Could we just talk about it? And I said something about churches. And then,
Okay. It is where subduction occurs. It's also the ocean crust is meeting the continental crust there, right? Because subduction occurs where the 2 meet. So both of these are correct.
Now I don't feel so dumb.
Go ahead.
Correct.
No, because they're equivalent. The subduction occurs where the 2 meet. Now, actually, okay, I will say there is a better to this. I didn't point it out. You have to have subduction. The 2 can meet and not have subduction. What's going on right now in California is a transform. It's going like this instead of subducting. Right? You had that homework problem. How long will it take for Los Angeles to get to San Francisco at the current rate of motion? Yeah, 17 million years.
Hey, I got it.
But it's not subducting, so it's not going to be creating the trench. So the one where the ocean crust meets the continental crust is not complete. So actually there is a better one. The one that had where the subduction occurs is better because it is possible to have them meet and not have subduction. You could have them still. That wouldn't do anything. You could have them pulling apart, I suppose. That would make a different thing. Make a Rift Valley. Okay, moving on to a new topic. What causes ocean waves?
Were 2 ships that pass into life, and we smile as we say it's.
Yeah.
Mm-hmm.
Okay, Jackie Carmen. All right, everyone has answered. Our answers were none for the ships, none for the motion of animals.
Oh, darn.
What's wrong with you people? 4, 7, 5, 0, 2. All right, Larissa. We had no majority today. Tell us what you feel.
Okay, well, I said,
By the way, this has not been lectured on. This is based on your previous understanding.
I said B.
Okay. And
Because, okay, well, it's obviously not ships, and it's not the animals. I guess it could be wind blowing, but I think that currents come better. And then the moon controls the tides. I don't think the sun does anything, so that means it could be.
okay, moon is the majority of the tides. The sun is also a minority factor for tides. And so both the sun and the moon would be an answer reasonable for what causes the tides.
Right.
The correct answer here is wind blowing over the surface. Now, well, no, there is no shame in having the answer wrong. I haven't even talked about it.
Think about on a really windy day, like how big the waves are.
And the tides.
The difference between waves and tide. Tide is talking about the level of the ocean water. Waves is talking about things that come. Okay, so I just have to share this. I used to have a TA in this class, well, in my astronomy class, who went on to dental school, and I used to, until I married Amy, spend my summers out at Huntington Beach. So he came out to visit. We're out swimming in the waves at Huntington Beach, and he says, I was out here with a friend, and there was a freighter passing out there, and he's pointing to it and said, "Man, can you believe all these waves, the result of those ships out there? What would happen if there were no ships? You wouldn't have waves." My student looks at him, "Are you kidding me?" Right, a boat does make a wake. We know that. And this person had just said, boats make wakes. Those wakes then come on over to the shore, and that makes waves. So, back at the time of Christ, you would have had essentially no waves anywhere because they did have boats, but they didn't have big freighters going through the ocean.
When he caught the storm, it wasn't that the big storm. There weren't a lot of boats out there.
Well, I have to tell you, I was visiting my parents in the Philippines, and we went to a beach, and it had these little 8-inch swells. And I was out playing in the ocean, and I came in, and one of the Filipino guys there was there with his kids. And I said, "Hey, you guys should come in and swim in the ocean." He's like, "Oh, no, I don't like those big waves." Okay. They different perspective. I like big waves. So it's the wind blowing over the surface, and we'll talk about that. You had a question, Jocelyn?
Why is D not a thing?
Why is D not a thing? Currents running under the water is a thing. It's just not what creates the waves. Yeah, this is all of these things occur and have effects. The motion of animals in the water has a net effect of, averaging out to nothing, right? Ships moving in the water, sure, it does make little ripples for a while. Does not make the waves that come to us. It is wind blowing over the waters. The wind blows over the water, just like in making sand dunes, it's going to push the water. And so you have, let's look at the anatomy of a wave. These are all the words. It's much better to look at the picture. So you have the crest is the high point. The trough, look, crest is marked there, is the low point. You have a wavelength that's the distance between where the crests are, or the distance between the troughs. And you have a wave speed, how fast it's traveling. Question?
Is wind the only factor in those really big storms then too?
Wind is not the only factor, but it's the primary factor. Some other things that make a difference is if I go, actually I may not have the next picture in this sequence. When you get to shallow water, just like when I talked about tsunami, when it gets to shallow water, the wave slows down. And because it slows down, the energy has to go somewhere, it goes into stacking higher. So the waves get bigger as you get closer to the shore. And because the speed slows down, the separation gets smaller, so the wavelength decreases. So those are also factors, but the primary one is what's driving it, right? It's the wind that's driving it. So you have a big storm, you have high winds, drives a lot of waves. You get the storm surge, and you get the big erosion on MBA's beach, and you can see these rocks. Okay, to me it was awesome. You'll see I have a couple pictures of MBA later on in this presentation because that's my home I grew up in. Now, one of the things to notice about waterways, and if you've played in the ocean, you probably noticed this, stuff out there in the surf does not come flying in with each wave. It pretty much stays still, moving a little bit forward and a little backward with each wave. That's because these waves are actually circulatory. So if you look at a single molecule of water, here the black dot is showing a molecule of water. So if you have a wave pass, the molecule of water just goes around a circle. And so the waves aren't moving the water with the wave. The water moves as the wave passes, but it basically comes back to where it starts. So you have something bobbing on the wave, it stays about the same place. There will be some subtle motions, of course, some general drift, but they're not coming in with the wave. And that's kind of good because when you're out playing the surf, you would come crashing into the shore with each wave if that was what happened. Yes, Brittany. Those circles are to indicate the motion of the molecules of water. That the molecules of water, at this point, they're going in circles like this. Down here, they're going in smaller circles as you go down. So that's what those illustrate. So, this is still not the next picture. This just has already what I said. Okay, here is the closest thing I have to the follow-up picture. as you get closer to the shore starts causing drag on the circular motion at the bottom, and that's what causes things to back up and build up. So you can see the height of the crest here is moving up. And so you finally get to where the water on the top is moving forward fast enough compared to the water on the bottom that you form the breaker that comes over. So the breakers occur because of the slowing of the water that's caused by making it more shallow. So if you just have deep water coming to shore, you don't have these waves build up. But the shallow is where they build up. And so, when surfers are out there surfing, the place where they get the good waves is where you have this action on the floor. So sometimes you'll have it go like this again. And so they're out here surfing here, and you have a large distance from there to where the beach is. Yes, surf is the name for the crashing stuff here. Just thought I'd get that out there. Now, there's a lot of interesting things. Yes, Brittany again.
So can you look at your picture?
Yes, ma'am.
So the waves that are in the deeper water are smaller than the waves.
Yeah, they build up when you get to shallower water.
Because there's more distance.
When it's deeper, there's less resistance for the water to flow, right? Because the water's going like this, there's less resistance to that. When it gets shallower, you have more resistance, and that slows it down and makes it build up. Okay, interesting things that happen with waves. When the waves come in, they usually come in pretty much straight into shore. Why pretty much straight into shore? The same reason that the lens works when you wear something like eyeglasses. When you go into the shallower water, the waves go slower and they bend into the slower region. And so waves coming in, see that effective wave direction? They actually tend to curve in like this. And so they generally come in pretty close to straight into the shore. But if they're not coming straight into the shore, they're going to move the sand along in the direction that it's going that's parallel to the shore. And so you can make it depletive sand over here and deposit a bunch of sand over there based on the direction the waves are coming. Now, because of that refraction is what we call the bending when it goes into the slower material. If you have something here that has coves, because it's getting shallow here, the waves tend to bend in, and they will do more erosion on the headlands and less erosion here in the cove. So the cove is generally protected because the waves refracted away from the cove and into those headlands. Well, in terms of erosion, that means you're going to have more deposition in there in the cove, building up a bigger beach, and more erosion in the headland, bringing it back. So eventually, over time, those will expand and flatten out to give you nice big beaches. Which is good to know, right? Over time, beaches form. So here's what a beach looks like. This is the picture they gave us. This, of course, reminded me of a beach there in Santa Cruz where we used to go for grade school picnics. But something arches, I don't even remember anymore. And so that made me look at the pictures of where I grew up. So here's a picture of, Dan Zinke and Josh Rosato and Elder Voth, Harvey Voth. I'm pretty sure I'm not in this picture. There's Mrs. Register, who sadly is dead. Yeah. But why do I have this picture? It's not so I can point out all of these people. She was the mother of my sister and brother's best friends. They lived across the street from us. On our beach there at Monterey Bay Academy, we have this here, the bluff. Everybody MBA knows about the bluff, and you go through the cut. The cut is in this picture right over there to get down to the beach. The bluff, you can see here, this is MBA's beach again. You can see the runway. Here's where they have the, Actually, yeah, it used to be pterodactyl when I was there, but I'm pretty sure it's the rainbow fins in that location now. If you're a surfer, you can get a rainbow fin that's made there at Monterey Bay Academy. Here's the bluff again. And you can see signs of erosion. When we have big storms, the ocean water will come up all the way to the bluff and erode things out. And then you'll have things fall down from the top of the bluff to the bottom because of the erosion that's occurred at the bottom. Other things that are really, really important. There's the barn I helped build when I was a freshman in high school. We don't have a dairy there anymore, so they now use it for horses, but it's important to know. And remember we learned about water treatment? Yeah. Those are the sewer ponds. So that's Monterey Bay Academy. An example of what the ocean looks like. So you have the terrace here, right? Monterey Bay Academy is up on a flat terrace. You can see it's a nice flat region there. And then you had erosion making the bluff, which here is called the Sea Cliff, which is why we have Sea Cliff Beach just down the road from MBA. We do not have any sea caves in our area because it's not a strong soil. It can't really maintain a cave. And we don't have any arches because those occur once again in a rock. And sea stacks are the remnants of an arch that's been eroded away. So just some features in oceans. If you go to SoCal camping, like I will again this summer, you can go down there to the beach and, Capitola Beach. You can play there and have a lot of fun.
You go to SoCal camping?
Of course.
Literally never seen you.
Well, I did every year until I got married, and then finally last year I got my wife to go, and she loved it so much that now we're going to go every year again.
I have a question about the Sea Cliff. Is that the same thing as the bluff?
Yes. Yeah. Okay. Other things. I don't know why, but the lagoon is always just makes me think of Disneyland, Gilligan's Island, because they're on a lagoon. The lagoon here, if you look, is separated by a sandbar. So it tends to be swampy. Once again, if you go out there to the beach at Capitola, actually, trying to think, not there where Mr. Toots is and whatnot, but there's a nice lagoon with tide pools that you can go enjoy. Beach, inlets. Hey, these are just all important to me. What's a barrier island? It's an island that forms a barrier. Very nice. It's where you had sand that was dragged out and deposited somewhere away from the shore. And so you can form a barrier out here. It may not reach the surface, but if it reaches the surface, it's barrier island. And that would, of course, stop waves from coming in. So we have the barrier island here, but you can have them further out. During storms, we will have situations that create barrier islands at Monterey Bay Academy, which is kind of cool, but they dissipate quickly. Yeah.
Did Raquel just ask if a bluff is the same thing as a beach?
No,
Okay.
as a sea cliff.
Oh. As a sea cliff.
Yeah. Okay, coral reefs. Coral is an animal, right? The coral reefs are made by the secretions of these little sea creatures that lithifies, forms rock, forms calcium carbonate. And so coral reefs are living things because the coral in there is living and producing new material. Now, as ocean temperatures rise, the acidity of the ocean becomes greater and it starts damaging the coral reefs. And so we have the example here, coral bleaching. When the coral turns nice and brilliantly white, that's an indication of global warming because of the higher acidity of warm water. So the coral reefs, I mean, if they disappear, that means we killed the species, right? So we don't want that to happen. And so the warmer waters are
are harsh on them and kill them. Question.
Like, what about the whole like higher specific heat capacity? Like, has the temperature really gone up like that much?
When we talk about global warming, the temperature changes we talk about are small numbers. Like 1 degree Celsius is an immense change in temperature in terms of global warming. So it hasn't gone up by that much as you and I would account it because it has a high specific heat. But that's a lot of heat that had to go into raising it. And so that goes into the accounting of what's happening to the global temperatures. If we have more thermal energy, we heat it up. And so just a few degrees difference in ocean water makes an enormous difference. California was in that long drought that ended this year. And that long drought was because there was a hot spot out there in the ocean, just a couple degrees elevated, but a couple degrees is a huge increase. And that changed the entire weather patterns. Okay, so talk about tides, right? We had that slide about what caused waves before we talked about it. Now we know the answer. What causes waves? Wind, right. Wind causes waves. The waves get pushed the direction the wind's blowing. Well, tides are caused primarily by the moon, by the moon's gravity. Now, something I don't pick on much, or I don't select much. Sharon, tell me about the gravitational force. What things come to your mind about gravitational force? Is it not Sharon? Is that your sister? Yeah. Ms. Adams. Dang it.
Yes.
Stacy. See why I never call on Stacy? Because she's not Sharon. So sorry. So Stacy, tell us what you know about gravity. Yeah. Okay, that's the acceleration of gravity, but the force. Well, for Earth it is, but talk about the gravitational force between you and Jocelyn. What direction is the force on you because of Jocelyn? Okay, it's attractive. So you're being pulled toward Jocelyn. Now, how's the force of Jocelyn pulling you compared to the force of Hannah pulling you? Okay, so Hannah being farther away is a weaker force. The equation is the force of gravity is G mass 1 mass 2 over the separation squared. So we have the moon here, and we're just going to take a little parcel of Earth or water, depending on where we are. And if I take those three little parcels, if each one has the same mass, which one has the strongest attractive force to the moon?
I want the least separation.
The one with the least separation, the one that's closest. So this one here has a force indicated by this arrow that's bigger than the force on this one with the small arrow. And in the middle, it would be an arrow that's somewhere in between. So we call this a differential. That's not it. A differential force because it varies in strength by where you are going across the Earth. And because it's varying with strength, what happens, varying in strength, what happens is the average pull on the Earth is what you have there at the center, but the stuff that's closer is pulled harder. And since water is a fluid, it can easily deform, and it gets pulled out away from the Earth. And so that's what the tide is, that the level of the water is changing. So you have a high tide on the side that's closest to the moon. Well, what about on the far side? What's going on there?
It's being pulled the opposite.
Okay, it's not being pulled as hard. So if you take the center and say that this is my average, then it's compared to the average, it's the opposite direction. So it's not being pulled as hard, so it starts stretching away because it's inertia trying to keep it out there. And so you have high tides both on the side closest to the moon and farthest from the moon. So we have two high tides at all times. One on the side nearest the moon, one on the side farthest. Then we get to some effects that I'm not even sure the textbook talks about. The Earth is rotating. So we have the Earth is rotating like this, and then we have the moon that's going around like this. Because the Earth is rotating, and the Earth rotates, it does one complete rotation in 23 hours, 56 minutes and 4 seconds or something like that. It's 57 minutes. Just under 24 hours to do one complete rotation. Whereas the moon takes 27.3-ish days, somewhere in that ballpark, to do one orbit around the Earth. So if you have a high tide that builds up here, the Earth's rotation pulls that forward. And so it turns out that the high tide, because of the Earth's rotation, is a little bit ahead of where the moon is. And likewise, on the other side, the high tide will be a little bit ahead of opposite. Brittany.
Can you determine how quickly the Earth rotate, but depending on how high the tide is, like where the Earth's rotation?
The tide variation in when high tide occurs has to do with both the Earth's rotation and the moon's rotation, orbit around the Earth. So it's a combination of the two. You can't determine one alone. You have to at least know what one is.
Where the moon is based on where the tide, how high the tide is.
You can, and there's some other things in it as well. So let me finish talking about this, and you'll probably understand it better. So the high tides actually lead the moon by just a little bit. But because the high tide leads the moon by just a little bit, that means that the force is not directly to the center, but actually is pulling it forward a little bit. So the high tides of the Earth pull the moon forward. As they pull it forward, we have a force that's parallel to its motion, doing work on the moon, transferring energy. So we are slowly transferring energy to the moon, which makes the moon go faster, which makes the moon go farther away from the Earth. So the moon moves away from the Earth. I think the distance is something like 1/4 of an inch a year. Don't quote me on that. I didn't look it up. But the moon is very slowly moving away from the Earth. So in the course of millions of years, the moon will be much farther away than it is now, which I find totally cool that we have something this interesting going on. Now, I said the sun also plays an effect. So we have the sun out here. The sun is very, very far away. The force of the sun on the Earth is far greater than the force of the moon on the Earth. But because it is so far away, the differential force, the difference in the force of the sun on one side of the Earth compared to the force of the sun on the other side of the Earth is a much smaller. It's something like 1/5 or 1/10 the strength of the moon's variation. So the sun also makes an effect on the high tides, just a much smaller effect. But that gives you a cycle for high tides. Because when the sun and the moon form a straight line with the Earth, so when you have sun, moon, Earth, or sun, Earth, moon, either one of these, then the high tides caused by the sun are the same place as the high tides caused by the moon. What's that going to do to the overall tide? If they're the same, it's not going to cancel. It's going to make it bigger. So when they're lined up like this, you have bigger tides, which we call spring tides. Spring tides are the big tides. And when they're at a 9-degree angle, so when you have sun, earth, moon like this, then they do what you were saying. Because the moon is saying high tide should be here, the sun's saying they should be here. They work against each other, and you have smaller tides, and we call those neap tides. So that's your smallest high tide to low tide variation occurs at the neap tide. Your largest high tide to low tide variation occurs at the spring tide. So like if you're a surfer, you're paying attention to when you have your high tide and when it's spring tides, because those are things that tell you, this is going to be good surfing conditions, or so I believe, because I don't surf. Okay, already talked about everything on that. Talked about that as well. So you got the word neap tide there, word spring tide there. We will stop here rather than starting in on the atmosphere. There there are a few more things to say. I didn't talk about the ocean currents. They'll come back. They're the last page of the chapters where it talks about the ocean currents. But there are currents of water that flow under the surface of the ocean that have a very big impact on our weather systems. We tend to think the weather is always above the earth and don't worry about the water, but the water is driving because it is a source for absorbing or giving off energy. Okay, have a great